Far
Right.
gone. Too far gone, to be honest.
Does that mean high?
What?
You're high?
Pardon?
Are you recording this?
Yeah.
All right, so I would like to get through those two things. If we just get through the math review and maybe a part of the other thing, that's okay. On Tuesday, we'll do whatever's left. I'm planning on having a session on Wednesday. I'm not allowing any of my freshmen to come in on Wednesday. I just want you guys to come in on Wednesday. So I would like you to plan Wednesday, 7:30. If you show up later, that's okay too, but I'm gonna put you on the list. This goes for anybody who's taking the test or anybody who's not taking the test. In other words, everybody. I expect you to show up here. If you have other commitments from other teachers, from other classes, your lesser classes, yes, you can do some of those. If they're super important that you have to be there or whatever, you can come in and out of here. So we're just gonna have like a review spiel going on Wednesday. And the types of things we're gonna do then are, well, first of all, whatever's left that we didn't cover in terms of reviewing that I wanna do today and Tuesday. And possibly going over the free response that I assigned to you, those 1 through 29. We'll go over some of those. I'm in the process of making an answer key for that, but I haven't quite figured out exactly how to format it the best way. So I'm struggling with the way the College Board formats their stuff. It's really user unfriendly, but I'll do my best. Ideally, we're going to go through the free response on Tuesday already and talk about those. Maybe not all of them, but a few of them I think are worth covering. And then, other than that, that's going to be it. Those people that are not taking the test, so if you are opting out or whatever, come to class like normal on Friday, and I'll have something for you to do in lieu of the test. I'll have some kind of a test for you to do. I'm not going to like grade it and make it ruin your grade or anything like that, but I want you to kind of have that experience of a pseudo AP test. Yes, sir?
Because we have to test in the morning, do we still come here for 7,000?
Well, I don't know if you're going to be done. Like, you're going to be done at what, noon?
Yeah.
You theoretically could show up then. You could tell me how it went. Well, I usually make the kids come, but with the way the schedule is now, with the block scheduling, is I don't know how it's going to work out with timing and lunch and all that stuff. But if you're here and you want to come, that would be nice. I mean, if you're dying and you got to go home and take a nap, I'm not going to hold it against you. But at some point at like a debriefing, we're not allowed to talk about the content of the questions, but you can tell me roughly how it went, how you feel about it. So, and how mad you are at me for not teaching you correctly or whatever. So, anyway. All right. Let's take a look at this math stuff. We started already with water potential, so, I mean, if anybody has questions, fine, but otherwise I would just say we've covered that enough. Oh, I put an answer key for all of this on Google Classroom in the same place as the assignment. It's just a second file that has the answer key. So theoretically, you could just go to the answer key right away and have all the answers and then never do this, but that's not really very productive when it comes to learning how to do this stuff. You know what I mean? The answer key is meant to be there for you to check to see if you did it right after you tried it on your own. All right, so we got a bunch of water potential stuff here. I guess these I did not do with you yet. So we could take a look at these. Did we do these yesterday, last time? I don't think we did. Right? We did the graph one where we found the solute potential of the egg of the plant cell, yes? Huh? Zucchini. So we did that one. And we know how to calculate solute potential. We remember that we have to change temperature to Kelvin.
That's cool.
You remember that I is the ionization constant. So that depends on if you have salt, it's going to be 2. If you have sugar, it's going to be 1. Does that ring a bell though? So which one's 2 ions or 1 ion? All of that stuff. C is just the concentration in molar. And then R is a constant that's going to be given to you. 0.0831. It's in bars instead of atmosphere, so it's slightly different than the Chem one. Have you guys done gas laws in Chem?
No.
Not yet? Okay. All right, I don't know if I can write on this. Let's see if it lets me. It does. Okay, so we're good. All right, so we have let's say that cellular concentration is 0.25, so I would right away have to plug this into my little formula and figure out what is the solute potential on the inside. So why don't we all do that right now, and let's see if you get the same number as I do. If temperature is 20, the concentration of solute on the inside, we'll assume it's sugar, so we're not going to say that, that I is 2, we're going to say it's 1. Let's assume it's sugar. You guys know what to do? You're looking at me like you're scared. Are you? Are we? Okay, good. Fine. I'll write it down. This is what we're calculating. Solute potential inside of the cell. Negative ICRT. Okay, go ahead and do that. I'll make some space here. That is a nice one. I almost don't want to erase that. Y'all remember this stuff?
No.
You guys know what this is?
Yes.
What's it called?
Chi-square.
Nice. All right, so I did not do it now, but did anybody get the number? Negative 6.3 is it or something? I don't know what it is, I'm just guessing.
Negative 6.09.
6.09, okay, I was close. So we know the inside is negative 6.09. The pressure is 2. Tells us that temperature is 20. Okay, that we already don't need. Okay, so we got negative 6, and we got 2, so it's going to be negative 4.09. Did I do that right? Yeah. The inside pressure potential, or so I'm sorry, water potential is negative 4.09. On the outside, we have distilled water. Okay, solute potential held, 0. Pressure potential is 1. So it doesn't say that, but we're going to assume atmospheric pressure is 1 bar, which is usually what it is. And then out is going to be 1. All right, so which is greater, 1 or negative 4? 1 is greater, so what's going to flow? It's going to flow in. So you write that down in a sentence. If you're actually answering this question on an AP test, you write a sentence, water flows in because water potential of 1 on the outside is greater than water potential of negative 4 on the inside. And then we're supposed to do like before and after. So what's going to happen is, the outer stuff isn't going to change because the cell is tiny and the beaker is big and it's got a lot of volume. So this is still going to be 0, 1, 1. That's going to be the same. But at the end, there's not going to be any more net water flowing back and forth. Okay, so here's what gets a little tricky. People get confused about this part. Like, how do we know what numbers to put in here? Because you just have to kind of estimate what you think might happen. But there are certain numbers that you don't get a choice. You have to have the right number here to make this correct. So the water potential on the inside has to be the same as the outside because water is not flowing anymore. But it's going back and forth in and out at the same rate. So we know this is going to be 1. So now we have to make something up here. Something's going to change with these. What do you think might happen to the solute potential if we're mixing more water in with the sugar that's in there? Is it going to become more dilute or more concentrated? More dilute, which means this should go more negative or less negative? Less negative. So I'm just going to make something up. I'm just going to say negative 5. That's reasonable. Anything is reasonable here as long as you're going closer to 0, not more negative. Because if you're going more negative, you're implying that this is getting more concentrated. That's not. Okay? And you also know this has to be 1 because no more water is flowing back and forth. So that tells you then what the pressure is going to be. Now you can calculate that. Negative 5 plus what is 1?
6. Well, can you fix your answer?
What's wrong with it?
You just put 0 instead of 1. Would it be 0?
For this?
No, for the pressure on the outside.
Oh, no, the pressure on the outside is not 6. The pressure on the inside is...
No. On the answer key, it says the pressure on the outside is 0.
Oh, that's the same. You can do the problem that way too.
But we get like
That's-
points
No,
down.
no, you would have to be told what to use for that pressure. If
Okay.
you can use zero on inside and outside if you want to. If it's an animal cell, you could just do zero because it's gonna be the same. The only time it matters if it's a plant cell, there's gonna be some turbo pressure. But whether you use 1 or 0 here, I don't really care. It doesn't matter, because we could make this 0 and then we could just make this like 1 instead, you know, it would come out the same idea.
AP doesn't hurt, the AP.
No, they're not gonna ask you anything that tricky.
Okay.
They're not gonna be that picky about it. If they give you a water potential problem, it'll be easier than this.
For real?
Okay, I'm giving you harder stuff just to prep you for anything. But yes, so I was scared that I had this wrong. No, I'm not worried about this, but 1 is more realistic because atmospheric pressure actually is 1 bar. It's not gonna be 0 because that's like outer space where there's no pressure at all. So, anyway. Okay, so are we clear on that? What does that tell you about the pressure inside the plant cell, the turgor pressure? If it's in distilled water, the turgor pressure will go up a little bit, right? It's gonna get pretty pressurized. Might bulge a little bit, but it's not gonna explode. All right, glucose, so 2 molar, you'd have to do the calculation. All right, I'm gonna do it. You do it too. So now we got 2 molar, so we can't just make up a number, we have to use the 2 molar. So I'm gonna say -1 times 2 times R times the temperature, which is still 293. Holy crap, holy, look at that. That's -48.7. Anybody else get that? You with me? -48.7, okay, so pressure on the inside we were told is 2. Water potential is then going to be -46.7. All right, solute on the outside. Oh, I'm sorry. Okay, that's my mistake, that's wrong. I'm talking about the outside solution is 2 molar. Okay, so this is negative, what did I say it was, negative?
48.7.
48.7 was it?
Yeah.
All right, so sorry about that. This is still the same, -6.09, that's the same. Pressure we said was 2, so it's -4.09. Okay, pressure on the outside is going to be 1. Water potential on the outside is going to be -47.7. Okay, so now we have to decide it's going to go in or out. Water in or out?
Out.
Water is going to go out because -4 is greater than -47. Does that make sense? All right, so water's going to flow out. You've heard that in a sentence. You've explained why. Here comes the tricky part. The cell's going to shrink. Osmosis is going to take place. So on the outside, we're going to do the same thing here. We're going to say this is -48.7. This is going to be 1. This is -47.7. And now we have to decide, okay, no more water is going in or out. That means this has to be -47.7. Okay? This is no longer pressurized. So what is this pressure now? So on the key, if it says 0 here, you would put what here? 0. If it's 1 here, you put 1. So what does that tell you this has to be now? -48.1. 0.7 I mean.
0.1.
Okay, so that's what it is then. Because what's going to happen is so much water is going to diffuse out that it's going to get more and more and more concentrated until it's the same as the outside, and then no more water flows back and forth. You understand that if you have a solution and you remove water from it, it's going to get more concentrated, and the solute potential is going to keep getting more negative. So that's how you know what those numbers are going to be. Pretty cool on that? All right, the only thing I'm going to say about the animal cell one, because I haven't, I'm not going to go over that much detail because I want to get through this stuff, is the, I get to do this? I would like to point out with the animal cell one that if you dump it in distilled water, this could theoretically burst. This might be a better problem if you let it burst, because then it's different than the plant cell, one we just did. So if you draw it where it bursts open, then everything equalizes inside and out, blah, blah, blah. But other than that, things are going to be very, very similar. The only thing is that there's no cell wall to collapse. All right? So So this thing could burst, so I would maybe draw it like this. You know, bursting open, and then all of this stuff is the same. You can check the answer key for the values that you're gonna get, and hopefully that'll be good enough. Is it okay if I don't go through this one step by step? Because it's very, very similar to what we just did with the math. All right? All right, cool, thank you guys. Moving on. Can I do that? All right, here we have a problem that I kind of like this one. It's dealing with epistasis. Can you guys refresh my memory what epistasis is?
No,
Isn't it something to do
Someone
with
say
like,
no.
I did.
Go ahead, Ben.
isn't it something to do with like one gene controls the other one? So
Yeah.
it's like color, like one shows color, one doesn't show color.
Yeah, so here's what it is. So one gene controls the other one. So the example we gave was pigment in mice, in the hair. Could be black or gray or brown. I don't remember what colors we used. What is this one? Is it mice?
Gray and white.
So it's black or gray, and then if they have, the second gene controls whether the pigment actually gets put into the hair. So here's one place where the pigment is produced, and then there's another thing that controls whether the pigment goes into the hair or not. So you can make all the black pigment you want. If it doesn't go into the hair, the color is going to be white. Everybody with me? All right, so that's what that's all about. And when you do this cross, you get a really strange Punnett square. It's your traditional 4x4. But what ends up happening is your ratio ends up being 9 to 3 to 4. So you get 9 black, you end up getting 3 gray, and you end up getting 4 white. Okay, and this one, this one, this one, and this one ends up being little b, 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 and that tells you that, oh boy, no pigment is going to get put in at all. Okay, so these normally would have been, I gotta think now. This one normally would have been white. Oh no, this one normally would have been gray. These guys normally would have been whatever. Oh no, I guess all of these guys would have been gray. So the point is that because this second gene ends up being the one that controls whether the pigment gets put in, you end up seeing 4 white, which is a really weird phenotype ratio. So if you see this, it's like, wait a minute, that doesn't follow anything that Mendel taught us. Something's weird here, something's odd, it's off. And it's because of epistasis. We'll go back in your notes if that's foreign to you right now, right, Buckner?
Yeah.
If it's confusing to you right now, go back into your notes. The book covers it really nicely. Talk about it or review it and do that. I don't want you to get so caught up on thinking that it's always going to be black, gray, and white. It's not. Like on my test for genetics, when we gave the test, I put a question on there with horns on some animal, some goats or some, I don't know, something with horns. And I said they could have straight horns or they could have bent horns. And if they have that second gene, homozygous recessive, they would have no horns at all. You with me? So that's totally different from the color. So it doesn't have to be white necessarily, it could be something different. Because on the AP test, if an epistasis problem pops up, and you understand epistasis, but you're so focused in on the color that you forget that, oh wait, it could be other stuff too. They'll come up with something you don't expect, like some other trait that you haven't thought about before, but it's still the same thing. And that's the ratio you're going to see. All right? Now, it's a chi-square problem, so I'm not sure I want to go over the whole chi-square spiel, but what I will do for you is just show you how to get set up, and I'm not going to work through the whole thing. We got 105, we got 38, and we have 0.7, so that's supposed to be our 9 to 3 to 4, right? So what you're gonna, that's your observed, and then you're supposed to figure out expected. Well, the way we figure out expected is, how do we do that? We get the total. Okay, what's, oh, I don't want, can somebody help me? Do the total. How do we get expected though, once we know the total? have to have a fraction.
190.
Say what?
190.
So the total's 190?
Yeah.
Okay, that's confirmed by everybody else. What do I do with the 190 here then to get the expected?
105.
Louder?
105 divided by, wait, no, very wrong. You
No, ignore this for now. We got the 190. Focus on this now.
9/16.
9/16. 9 out of 16. How do we know that? Because this is 9 out of a total of 16. See, 9 plus 3 is 12, plus 4 is 16. It's 16 total. 9/16 of them, of 190, should be this phenotype. Okay? So whatever that ends up being. What do I do here?
close. Oh, you do this one.
3/16 times 190, and over here,
4/16.
4/16 times 190. So we, whatever that ends up being, then we can start the chi-square thing where we say observed minus expected. So can somebody do this real quick here? 9 divided by 16 times 190.
106.9.
All right, so we say observed 105 minus 106.9. That's actually really close. Look, it should have been 106.9 and that was 105. That's very, very tight, very close. That means your chi-square value is going to be really small for that one. That particular chi-square is going to be really, really small. These other ones might be off a little bit more or whatever, but that's what you do. You do the 105 minus 106.9, observed minus expected square divided by 106.9. And then you figure that out for this one, you add them all up, and then you compare it to the critical value on the on that table, which you will be given. Which certainty do we go by? 0.01, 0.05, 0.05, we go to 0.05, and we have how many degrees of freedom here? We have 3 phenotypes, 2 degrees of freedom, because you have phenotypes minus 1. So you look at that number, I think it's 5.991 or something. You check that out, and you'd say my chi-square of, I don't know, I'll get like 1.73, I'm just making this up, is less than 5.991. Therefore, the differences between our numbers and a true 93:4 ratio are just due to chance. College Board likes to talk about a null hypothesis. The null hypothesis is that the differences between the observed ratio and the actual ratio that we're predicting, or the predicted ratio, is just simply due to chance. That's okay. It's still close enough that it's a 93:4. That's what we're saying here. The differences between this and an actual 93:4 are just due to chance, which means it's perfectly fine. It's just a statistical fluctuation, and there's nothing wrong. It is truly a 93:4. With me? So if you see null hypothesis, don't freak out. That's just saying, what they're saying is that basically these numbers are not so far off that it's no longer a 93:4. They're saying that the difference here, 106.9 from 105, that's just random chance, and that's okay. Does that make sense? All right. All right. Hardy-Weinberg, we're not going to go over again because we just did. All right, we did Hardy-Weinberg not very long ago. You guys comfortable with it?
Yeah.
There's one that's, it gives you a percentage, so that sometimes people get confused. They're like, I don't know what to do with that.